Picture this. You're holding a photograph of your childhood, trying to determine exactly when it was taken. You might look for clues, the clothes you wore, the car in the background, maybe a calendar on the wall. Scientists face a similar challenge when trying to determine the age of our entire universe, except their photograph spans billions of light years and contains the echoes of creation itself. The quest to understand cosmic time represents one of humanity's most ambitious endeavors. We're essentially cosmic detectives, sifting through evidence scattered across the vastness of space and time, trying to piece together the ultimate origin story. Every photon of light that reaches our telescopes carries with it a message from the past, a clue about when and how our universe began its remarkable journey. The story begins in 1929 with a man named Edwin Hubble, who made one of the most profound discoveries in human history. While peering through the massive telescope at Mount Wilson Observatory in California, Hubble noticed something extraordinary. Every galaxy he observed was moving away from us, and the farther away they were, the faster they seemed to be receding. This wasn't just a coincidence, it was evidence that space itself was expanding. But let's back up for a moment. Before Hubble's revolutionary observation, most scientists believed in a static universe, one that had always existed in roughly the same state. Even Albert Einstein, whose equations of general relativity actually predicted an expanding universe, was so convinced of a static cosmos that he added a mathematical term called the cosmological constant to force his equations to describe a universe that neither expanded nor contracted. When Hubble announced his findings, it sent shockwaves through the scientific community. Here was observational proof that the universe was not eternal and unchanging, but dynamic and evolving. The implications were staggering. If the universe was expanding now, then in the past it must have been smaller, denser, and hotter. Imagine you're on the surface of a balloon that's being inflated. As the balloon grows larger, every point on its surface moves away from every other point. The galaxies aren't actually moving through space. Rather, space itself is stretching, carrying them along like raisins in rising bread dough. This revelation gave birth to what we now call the Big Bang Theory, the idea that our universe began as an incredibly hot, dense point and has been expanding ever since. The term Big Bang itself was coined somewhat mockingly by astronomer Fred Hoyle during a BBC radio broadcast in 1949. Hoyle was actually a critic of the theory, preferring instead his steady-state model of the universe. But the name stuck, and ironically, the theory that Hoyle tried to ridicule would eventually become the cornerstone of modern cosmology. But Hubble's discovery gave us something even more valuable than just understanding expansion. It gave us a cosmic clock. By measuring how fast galaxies are moving away from us and how far away they are, scientists can calculate something called the Hubble constant. This number tells us the rate at which the universe is expanding right now. Think of it like determining the speed of a car by watching how quickly distant landmarks pass by. The measurement itself is remarkably elegant in its simplicity. Astronomers observe the light from distant galaxies and look for specific patterns called spectral lines. These are like cosmic fingerprints created when atoms absorb or emit light at very specific wavelengths. When a galaxy is moving away from us, these spectral lines get shifted toward the red end of the spectrum, a phenomenon known as redshift. The amount of redshift tells us how fast the galaxy is receding, while other observations help us determine its distance. When Hubble plotted velocity against distance for dozens of galaxies, he found a surprisingly linear relationship. Galaxies twice as far away were moving away twice as fast. This relationship, now known as Hubble's law, provided the mathematical framework for understanding cosmic expansion. Here's where it gets fascinating. If we know how fast the universe is expanding now, we can essentially run the cosmic movie in reverse. Just like rewinding a video of an explosion to see when it started, we can calculate backward to determine when all the galaxies were compressed into that initial, infinitely dense point we call the Big Bang. The mathematics are surprisingly straightforward. If we know that galaxies are moving apart at a certain rate, we can calculate how long it would take for them to have been at the same location. This gives us what's called the Hubble time, a rough estimate of the universe's age based purely on its current expansion rate. Using this method, scientists initially calculated the universe to be somewhere between 10 and 20 billion years old. But that was just the beginning. As our instruments became more precise and our understanding deeper, we needed more sophisticated ways to measure cosmic time. The early estimates had significant uncertainties because measuring distances in space is notoriously difficult. The first rung of this ladder involves measuring distances to nearby stars using a technique called parallax. As Earth orbits the Sun, our viewpoint shifts slightly, causing nearby stars to appear to move back and forth against the background of more distant stars. It's the same effect you see when you close one eye, then the other, and watch how your thumb seems to jump against the background. The smaller the apparent movement, the farther away the star. This technique works well for stars within a few hundred light years. But beyond that, the parallax angles become too small to measure accurately, even with our most sensitive instruments. So astronomers had to develop other methods for greater distances, each one calibrated using the previous techniques. For more distant objects, astronomers rely on what they call standard candles, objects whose intrinsic brightness is known or can be determined. By comparing how bright these objects appear from Earth with how bright they actually are, astronomers can calculate their distance. It's like trying to determine how far away a light bulb is by measuring how bright it looks, if you know the wattage of the bulb. One of the most important types of standard candles are Cepheid variable stars, pulsating giants whose brightness changes in a regular, predictable pattern. In 1912, astronomer Henrietta Swan Leavitt discovered that the period of these pulsations is directly related to the star's intrinsic luminosity. Brighter Cepheids pulsate more slowly than dimmer ones. This period luminosity relationship became one of the most important tools in cosmic distance measurement. Hubble himself used Cepheid variables to measure distances to nearby galaxies, including the Andromeda Galaxy. His observations confirmed that these spiral nebulae, as they were then called, were actually separate galaxies, far beyond our own Milky Way. This discovery alone revolutionized our understanding of the scale of the universe, revealing that we lived in just one of countless galaxies scattered throughout space. But even Cepheids have their limitations. Beyond a certain distance, individual stars become too faint to observe clearly, even with powerful telescopes. For the most distant galaxies, astronomers turn to even brighter standard candles, entire exploding stars called supernovae. Type Ia supernovae are particularly useful because they all reach roughly the same peak brightness when they explode. These stellar detonations occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass and explodes in a thermonuclear blast visible across billions of light years. Enter the cosmic microwave background, or CMB, perhaps the most important baby picture ever taken. When the universe was only about 380,000 years old, it had cooled enough for the first atoms to form. Before this moment, the universe was so hot that electrons and protons couldn't stay together. They kept getting knocked apart by high-energy photons. But when things cooled down enough, these particles finally combined to form the first hydrogen atoms. To understand why this moment was so crucial, imagine trying to see through a dense fog. Before recombination, the universe was like that fog, opaque to light because photons couldn't travel very far without hitting a free electron and being scattered in a random direction. The universe was literally dark, not because there was no light, but because light couldn't propagate freely through the dense plasma that filled all of space. This event, called recombination, was like turning on the lights in a previously opaque universe. For the first time, light could travel freely through space without being immediately absorbed or scattered. The afterglow of this moment is still visible today, filling the entire sky with a faint radiation that we can detect with sensitive instruments. But here's what makes the CMB so remarkable as a cosmic timepiece. The temperature fluctuations we see in this ancient light are directly related to the density variations that existed in the early universe. These tiny irregularities, typically varying by only a few parts in 100,000, were the seeds that would eventually grow into the large-scale structure we see today, the galaxies, galaxy clusters, and vast cosmic voids. The physics underlying these fluctuations is incredibly well understood. We know exactly how sound waves propagated through the primordial plasma, how they were affected by the density of matter and energy, and how they should appear to us today after nearly 14 billion years of cosmic expansion. This gives us multiple independent ways to measure not just the universe's age, but also its composition and geometry. The Planck satellite, launched by the European Space Agency, spent 4 years mapping this cosmic microwave background with unprecedented precision. The satellite's instruments were so sensitive that they could detect temperature differences of just a few millionths of a degree. By analyzing tiny temperature variations in this ancient light, scientists can determine not just the age of the universe, but also its composition and geometry. The patterns in the CMB are like cosmic fingerprints, each tiny fluctuation telling us something about the conditions in the early universe. Think of the CMB as a snapshot of the universe when it was just a baby, only 380,000 years old, compared to its current age of nearly 14 billion years. The patterns we see frozen in this ancient light tell us about the universe's vital statistics at that early epoch, its temperature, density, and rate of expansion. Through this analysis, researchers arrived at our current best estimate. The universe is 13.8 billion years old, give or take about 100 million years. This might seem like a huge uncertainty, but in cosmic terms, it's incredibly precise, like measuring the age of a centenarian and being accurate to within a few months. The precision of this measurement is truly remarkable when you consider the complexity of the physics involved. We're essentially using quantum mechanics and general relativity to analyze light that has been traveling through space for nearly the entire history of the universe, and we can determine the age of everything that exists to within less than 1% accuracy. What makes the CMB revolutionary is that it doesn't rely on the complex distance measurements that plagued earlier methods. Instead, it's based on fundamental physics principles we can test in laboratories. The ancient radiation has been stretched by cosmic expansion, cooling from the intense heat of the early universe to just 2.7 degrees above absolute zero today. The discovery of the CMB itself reads like scientific detective story. In 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate a persistent background noise from their radio antenna. No matter where they pointed their instrument, they detected the same faint microwave radiation. Initially, they thought it might be interference from urban sources, or even droppings from pigeons that had nested in their equipment. It was only when they consulted with theoretical physicists that they realized they had stumbled upon one of the most important discoveries in cosmology. The radiation they detected was precisely what the Big Bang theory predicted should still be observable today: the cooled remnant of the intense heat from the universe's birth. Penzias and Wilson had inadvertently found the afterglow of creation itself. Beyond the CMB, astronomers developed complementary techniques to cross-check their cosmic timeline. White dwarf dating offers a completely independent approach. These stellar remnants are like cosmic refrigerators, starting incredibly hot at 50,000 degrees Celsius, but steadily cooling over billions of years with no internal heat source. Since we understand white dwarf cooling physics precisely, measuring their current temperature tells us how long they've been cooling. The oldest white dwarfs in our galaxy clock in at 12 to 13 billion years, providing crucial confirmation of our cosmic age estimates. Globular clusters reveal another layer of cosmic history. These ancient stellar cities, containing hundreds of thousands of primordial stars, orbit our galaxy like archaeological artifacts from the universe's youth. The stars within them formed together in a cosmic burst of star formation early in the universe's history. Astronomers use a clever trick called main sequence turnoff, dating to determine cluster ages. More massive stars burn through their fuel faster than lightweight ones. In any stellar population, the point where stars begin evolving away from their hydrogen-burning phase reveals the cluster's age. The lower the mass of departing stars, the older the cluster must be. This technique consistently shows globular clusters formed 12 to 13 billion years ago. Each method is like a different witness to the same cosmic crime scene, and they all point to roughly the same conclusion. The universe began approximately 13.8 billion years ago in an event of unimaginable energy and has been expanding and cooling ever since. The convergence of these different techniques gives scientists confidence that we're on the right track. When measurements based on stellar evolution, white dwarf cooling, cosmic microwave background analysis, and supernova observations all point to similar ages, it suggests that our understanding of cosmic time is fundamentally sound. But science is never static, and new observations constantly challenge our understanding. Advanced telescopes and more sophisticated analysis techniques continue to refine our measurements, sometimes revealing unexpected complexities. The universe, it seems, still has secrets to reveal about its own history. Modern cosmology has also revealed that the universe's expansion hasn't been constant throughout its history. For the first several billion years, the expansion was slowing down due to the gravitational attraction of all the matter in the universe. But then, something changed. About 5 billion years ago, the expansion began to accelerate, driven by a mysterious force we call dark energy. This acceleration affects our age calculations because it means the universe expanded more slowly in the past than it does today. If we simply extrapolate the current expansion rate backward in time, we would underestimate the universe's age. The discovery of accelerating expansion, which earned the 2011 Nobel Prize in Physics, required cosmologists to revise their models and led to our current best estimate of 13.8 billion years. Yet even as this picture seemed to solidify, new observations began to raise uncomfortable questions. Advanced telescopes started seeing things that didn't quite fit the standard timeline. Galaxies that appeared too mature for their supposed age. Stars that seemed older than the universe itself. Measurements of the expansion rate that didn't agree with each other. The James Webb Space Telescope, with its unprecedented ability to peer deep into space and far back in time, has begun to reveal galaxies that formed earlier than expected. Some of these distant galaxies appear surprisingly large and well developed for objects that should have formed when the universe was less than 1 billion years old. These weren't just minor discrepancies, they were hints that our cosmic clock might be running slow, or perhaps that time itself in the early universe didn't behave the way we expected. The very foundations of our 13.8 billion year timeline were beginning to show cracks, and those cracks would soon reveal something far more mysterious than anyone had imagined. Imagine you're an archaeologist, but instead of digging through layers of Earth to uncover ancient civilizations, you're peering through layers of time itself. Every photon of light that reaches our telescopes is a messenger from the past, carrying information about cosmic events that occurred billions of years ago. The deeper we look into space, the further back in time we travel, until we approach the very edge of the observable universe and the dawn of cosmic history. This is the realm where our most advanced telescopes operate. functioning as time machines that reveal the universe's infancy. But what astronomers are discovering in these deepest observations is challenging everything we thought we knew about cosmic evolution and the timeline of creation itself. The story of ancient light begins with a fundamental principle of astronomy. Light travels at a finite speed, roughly 300,000 kilometers per second. While this seems impossibly fast by human standards, the universe is so vast that even light takes considerable time to traverse cosmic distances. When we observe a galaxy 1 billion light-years away, we're seeing it as it existed 1 billion years ago, not as it is today. This cosmic light delay means that powerful telescopes can literally observe the past. The Hubble Space Telescope, operating since 1990, has spent decades collecting ancient photons that began their journeys when the universe was young. But Hubble's vision, remarkable as it is, has limitations. Its mirrors can only gather so much light, and its instruments can only peer so far into the infrared spectrum where the most distant galaxies reveal themselves. Enter the James Webb Space Telescope, humanity's most ambitious space observatory. Launched on Christmas Day 2021, Webb represents a quantum leap in our ability to observe the early universe. Its primary mirror, composed of 18 hexagonal segments, spans 6.5 meters across, giving it nearly 7 times the light-gathering power of Hubble. More importantly, Webb's instruments are specifically designed to observe in the infrared, where the light from the most distant galaxies has been stretched by cosmic expansion. This infrared capability is crucial for studying the early universe because of a phenomenon called cosmological redshift. As light travels through expanding space, its wavelength gets stretched along with the fabric of space itself. Light that began its journey as a visible blue or ultraviolet radiation becomes infrared by the time it reaches us, shifted toward the red end of the electromagnetic spectrum. The most distant galaxies Webb can observe emitted their light when the universe was less than 1 billion years old, during a period cosmologists call the Cosmic Dawn. This era should represent the universe's awkward adolescence, when the first galaxies were just beginning to form from the primordial gas left over from the Big Bang. According to standard cosmological models, these early galaxies should be small, irregular, and relatively simple structures. But Webb's first deep field observations revealed something extraordinary and troubling. Many of the galaxies it detected were far more mature and massive than theoretical predictions suggested they should be. These weren't the cosmic teenagers that models predicted, but rather sophisticated galactic cities that appeared to have developed with impossible speed. One of the most striking examples came from observations of galaxy JADE SG NZE11, observed when the universe was only 400 million years old. This galaxy appears surprisingly massive and well-structured for such an early cosmic epoch. Its spectrum reveals the presence of heavy elements like oxygen and carbon, materials that should have required multiple generations of stellar evolution to produce in significant quantities. The creation of heavy elements is a slow process in cosmic terms. The first stars in the universe, called population 3 stars, were composed almost entirely of hydrogen and helium, the only elements produced in significant quantities during Big Bang nuclear synthesis. These primordial giants lived fast and died young, exploding as supernovae and scattering heavier elements into space. Subsequent generations of stars incorporated these elements, creating even more complex chemistry through nuclear fusion in their cores. This stellar alchemy takes time, lots of time. Current models suggest it should require several 100 million years to produce the heavy element abundances observed in some of Webb's distant galaxies. Yet these galaxies existed when the universe was supposedly too young for such chemical evolution to have occurred. Even more puzzling are observations of supermassive black holes in the early universe. Webb has detected active galactic nuclei, powered by black holes containing millions or billions of solar masses, in galaxies that formed when the universe was less than 700 million years old. These cosmic monsters should not have had enough time to grow to such enormous sizes through conventional accretion processes. Black holes grow by consuming surrounding matter, but there are physical limits to how fast they can feed. As material falls into a black hole, it heats up and emits intense radiation that can actually push away additional infalling matter. This creates what's called the Eddington limit, a maximum rate at which black holes can grow through accretion. Starting from stellar mass black hole seeds of perhaps 10 to 100 solar masses, it should take well over 1 billion years to grow supermassive black holes through normal feeding processes. Yet Webb is finding these giants when the universe was only a fraction of that age, suggesting either that black holes can grow much faster than we thought, or that they started from much more massive seeds than current theories predict. Galaxy CEERS 2782 represents another challenge to conventional timelines. This system appears to contain a black hole with a mass of several million suns, yet it existed when the universe was just 570 million years old. The galaxy hosting this black hole shows signs of rapid star formation and chemical enrichment that seem inconsistent with standard evolutionary models. The problem extends beyond individual objects to entire populations of early galaxies. Webb's surveys have revealed that bright, massive galaxies were far more common in the early universe than simulations predicted. The cosmic evolution. Early release science survey found that the number density of luminous galaxies at high redshift significantly exceeds theoretical expectations. This abundance of early massive galaxies creates what astronomers call the impossibly early galaxy problem. If galaxies could form and grow this rapidly in the early universe, it suggests that either our understanding of galaxy formation is fundamentally flawed, or that the universe had more time for these processes than the standard Big Bang chronology allows. Some researchers have proposed that star formation in the early universe was far more efficient than in the modern cosmos. Perhaps the pristine conditions of the primordial universe, free from the heavy elements that can inhibit star formation, actually accelerated the process of turning gas into stars. This could help explain the rapid growth of early galaxies without requiring additional time. Others suggest that the first stars were fundamentally different from their modern counterparts. Population 3 stars may have been much more massive than typical stars today, burning through their nuclear fuel in just a few million years rather than billions. These stellar giants would have produced and distributed heavy elements much more quickly than current models assume. But even with these modifications, many astronomers struggle to reconcile Webb's observations with the 13.8 billion year cosmic timeline. The sheer number of mature galaxies in the early universe suggests a level of cosmic evolution that seems to require more time than the standard model provides. The situation becomes even more intriguing when we consider Webb's observations of galaxy clustering. Not only are individual early galaxies more mature than expected, but they also appear to be organized into large-scale structures earlier than simulations predict. Galaxy clusters and groups, which should take billions of years to assemble through gravitational attraction, seem to have formed with surprising rapidity. Galaxy cluster MAX 0416, observed by Webb at a time when the universe was only 2.4 billion years old, contains dozens of massive galaxies that appear to have already completed much of their star formation. This level of cluster evolution typically requires several billion years in modern simulations. Yet it occurred when the universe was less than 20% of its current age. These observations force astronomers to confront uncomfortable questions about cosmic chronology. Either the early universe was a far more dynamic and rapidly evolving place than we imagined, or our fundamental assumptions about cosmic time may be incorrect. The ancient light reaching Webb's mirrors whispers of a universe that may have had more time to evolve than our current models suggest. The implications extend beyond astronomy into fundamental physics. If the universe is older than we think, it could affect our understanding of dark energy, dark matter, and the basic parameters that govern cosmic evolution. The carefully calibrated timeline that seemed so secure just a few years ago now faces challenges from the very observations it was designed to explain. As Webb continues its observations, pushing ever deeper into cosmic history, it may force us to reconsider not just the age of the universe, but our entire understanding of how cosmic structures form and evolve. The ancient light carries secrets that we're only beginning to decipher, and those secrets may ultimately reveal that the universe has been keeping time in ways we never imagined. Could the universe have had more time to craft these elaborate cosmic structures than our 13.8 billion year timeline suggests? The answer may lie hidden in the spectra of distant galaxies, waiting for astronomers to decode the messages carried by photons that have traveled across most of cosmic history to reach us. Deep in our galaxy's halo, floating like ancient sentinels in the darkness between spiral arms, are stars so old they remember the universe's childhood. These stellar relics have been burning steadily for over 12 billion years, their nuclear fires sustained by fuel that formed in the immediate aftermath of the Big Bang. They are the cosmic equivalent of living fossils, preserving in their atmospheres the chemical signatures of a universe that was radically different from the one we know today. But some of these ancient stars have posed a fundamental challenge to our understanding of cosmic time itself. For decades, astronomers measured stellar ages that seemed to exceed the age of the universe, creating paradoxes that forced scientists to question either their stellar dating techniques or the cosmic timeline itself. The story of stellar age determination begins with our understanding of how stars burn their nuclear fuel. Unlike a campfire that consumes wood and leaves ash behind, stars fuse light elements into heavier ones, converting hydrogen into helium, helium into carbon, and so forth up the periodic table. This process releases enormous amounts of energy, powering the star's luminosity for billions of years. The rate at which a star burns through its fuel depends primarily on its mass. Massive stars live fast and die young, burning through their nuclear reserves in just millions of years before exploding as supernovae. Lower mass stars like our Sun burn more conservatively, maintaining steady energy output for roughly 10 billion years. The least massive stars, red dwarfs, burn so slowly they can theoretically shine for trillions of years. This relationship between mass and lifetime provides astronomers with a cosmic clock. By studying the colors and brightnesses of stars in ancient clusters, they can determine which stars have exhausted their nuclear fuel and evolved away from the main sequence. The point where this stellar exodus begins reveals the cluster's age, much like counting tree rings reveals the age of a forest. The technique works because stars of different masses evolve at predictable rates. In any population that forms simultaneously, the most massive stars will be the first to exhaust their hydrogen fuel and begin evolving into giant stars. As time passes, progressively lower mass stars will join this evolutionary exodus. The mass of stars just beginning to evolve off the main sequence, called the turn-off mass, directly indicates the cluster's age. Using this method, astronomers have identified some of the oldest stellar populations in our galaxy. Globular clusters, those spherical collections of ancient stars that orbit in our galaxy's halo, consistently show ages of 12 to 13 billion years. These measurements provided crucial early evidence for the Big Bang model and helped establish the universe's age. But it was the study of individual ancient stars that created some of astronomy's most perplexing puzzles. In the 1990s, precise measurements of a nearby star, designated HD 140283 yielded an age that seemed impossible. This star, which became known as the Methuselah star, appeared to be 16 billion years old, significantly older than the then accepted age of the universe at 13.7 billion years. HD 140283 sits just 190 light-years from Earth in the constellation Libra. Despite its proximity, the star is too faint to see with the naked eye, shining at only 7th magnitude, but its modest appearance belies its cosmic significance. This star is a subgiant, a stellar evolutionary phase that occurs when a star begins to exhaust the hydrogen in its core and starts burning hydrogen in a shell around an inert helium center. The star's chemical composition tells a remarkable story. Its spectrum reveals extremely low abundances of elements heavier than helium, what astronomers call metals. The iron content of HD 140283 is less than 1% that of our Sun, indicating it formed from primordial gas that had been enriched by very few previous generations of stars. This chemical signature marks HD 140283 as a member of the galaxy's oldest stellar population, designated Population 2. These stars formed in the early universe when heavy elements were scarce, before successive generations of stellar nuclear synthesis had enriched the interstellar medium with the full periodic table of elements we see today. The age determination for HD 140283 relied on detailed stellar evolution models that calculate how stars of different masses and compositions evolve over time. By matching the star's observed properties, its temperature, luminosity, and chemical composition to theoretical evolutionary tracks, astronomers could determine how long it had been shining. The 16 billion year age estimate created a cosmic paradox. How could a star be older than the universe itself? Either the stellar age determination was wrong, or our understanding of cosmic chronology needed revision. The Methuselah star became a symbol of the uncertainties lurking in both stellar astrophysics and cosmology. The resolution came through multiple avenues of improved measurements and analysis. Better observations using the Hubble Space Telescope refined the star's distance and brightness, while improved stellar evolution models incorporated more sophisticated physics. Most importantly, the discovery of dark energy and the accelerating expansion of the universe revised the cosmic age upward from 13.7 to 13.8 billion years. With these refinements, the age of HD 140283 was revised downward to 14.5 billion years, with uncertainties of about 800 million years. While still uncomfortably close to the universe's age, the star was no longer definitively older than everything that exists. But HD 140283 was not alone in presenting age challenges. Other extremely metal-poor stars have yielded similarly ancient ages, pushing against the boundaries of cosmic time. The star Xi 1327-0326 appears to be over 13 billion years old, while CS 3108-2-001 shows similar antiquity. These measurements depend critically on stellar evolution theory, which must account for complex processes occurring deep within stellar interiors. Nuclear fusion rates depend on temperature, density, and chemical composition in ways that are sometimes difficult to model precisely. Small uncertainties in these fundamental processes can translate into large uncertainties in age estimates. One particularly challenging aspect involves the treatment of convection, the process by which hot material rises and cool material sinks within stars. Convective mixing affects how efficiently stars burn their fuel and how their surface compositions change over time. Different assumptions about convective processes can alter age estimates by billions of years. The presence of helium also complicates age determinations. While hydrogen and heavy elements can be measured directly from stellar spectra, helium absorption lines are typically not visible in the atmospheres of cool stars like HD 140283. astronomers must estimate helium abundances based on theoretical models of Big Bang nucleosynthesis and stellar evolution, introducing additional uncertainties. Beyond individual stars, entire populations of ancient objects have presented chronological puzzles. White dwarf stars, the cooling remnants of stars that exhausted their nuclear fuel, provide independent age estimates based on their cooling rates. The oldest white dwarfs in globular clusters appear to be over 12 billion years old, consistent with cluster turn-off ages, but adding another layer of evidence for extreme stellar antiquity. The discovery of hypervelocity stars has added yet another dimension to stellar age studies. These stars, moving so fast they can escape the galaxy's gravitational pull, may have been accelerated by encounters with supermassive black holes. Some hypervelocity stars show chemical compositions suggesting they formed in the galaxy's central regions over 10 billion years ago, providing constraints on the early evolution of the Milky Way's central black hole. Population 3 stars, the hypothetical first generation of stars in the universe, remain tantalizingly out of reach of direct observation. These stars would have formed from pristine primordial gas containing no heavy elements whatsoever. Theory suggests they were massive giants that lived brief lives before exploding as supernovae, enriching the interstellar medium with the first heavy elements. Finding a genuine population 3 star would provide a direct window into the universe's earliest stellar epoch. Several candidates have been proposed over the years, stars with extremely low metal abundances that might represent the most pristine stellar material. But none have been confirmed as true primordial objects, leaving this earliest chapter of stellar evolution shrouded in mystery. The study of the oldest stars also reveals the galaxy's construction history. The Milky Way appears to have assembled through a series of mergers with smaller satellite galaxies, each bringing its own population of ancient stars. By studying the chemical compositions and orbital motions of old stars, astronomers can reconstruct this galactic archaeology, identifying stellar streams and clusters that originated in disrupted satellite systems. Recent surveys using the Gaia Space Telescope have revolutionized our understanding of stellar motions and ages throughout the galaxy. By precisely measuring the positions and velocities of over 1 billion stars, Gaia has revealed complex patterns of stellar migration and mixing that occurred over the galaxy's history. Some of the oldest stars show kinematic signatures suggesting they formed in satellite galaxies that merged with the Milky Way billions of years ago. The chemical evolution of the galaxy also provides constraints on cosmic chronology. The abundance patterns of different elements in ancient stars reflect the nucleosynthetic processes that operated in the early universe. Rapid neutron capture processes, responsible for creating elements like gold and platinum, appear to have been more active in the galaxy's youth, possibly indicating a higher rate of neutron star mergers when the universe was dense and star formation was vigorous. As stellar age dating techniques continue to improve, they may yet reveal more surprises about cosmic chronology. New theoretical models incorporating three-dimensional stellar structure and improved opacity calculations promise more accurate age estimates. Future space telescopes may discover even older stellar populations, pushing closer to the epoch when the first stars ignited their nuclear fires. The ancient stars that populate our galaxy's halo remain active participants in ongoing cosmic evolution, their nuclear furnaces still burning after more than 12 billion years. They have witnessed the galaxy's entire history, from its chaotic assembly in the early universe to its current state as a mature spiral system. In their atmospheres, they preserve the chemical fingerprints of cosmic dawn, waiting for astronomers to decode the messages they carry about the universe's earliest chapters. Yet questions persist about whether stellar ages truly match the cosmic clock, or whether these ancient lights are telling us that time itself behaved differently in the universe's youth. The precision required to resolve these questions pushes both observational astronomy and theoretical astrophysics to their limits, revealing just how challenging it can be to determine the age of objects that have been shining since the cosmos was young. Picture two highly skilled watchmakers, each using the finest instruments available, attempting to measure the same cosmic timepiece. Yet despite their precision and expertise, they consistently arrive at different readings. One declares the universe is expanding at 73 kilometers per second per megaparsec, while the other insists the rate is only 67. This seemingly small discrepancy has profound implications, because it suggests our cosmic clock might be running fast, slow, or perhaps keeping time according to rules we don't fully understand. This is the essence of the Hubble tension, one of the most perplexing problems in modern cosmology. The tension arises from fundamentally different approaches to measuring how quickly the universe is expanding today, and the disagreement between these methods has grown more pronounced as measurements have become more precise. What started as a minor discrepancy has evolved into a crisis that challenges our understanding of cosmic evolution and the fundamental nature of space and time. The Hubble constant, denoted h0, represents the current rate of cosmic expansion. It tells us how fast galaxies are receding from each other due to the stretching of space itself. But this number is more than just a measure of expansion speed. It's a key ingredient in calculating the universe's age, size, and ultimate fate. Different values of the Hubble constant yield dramatically different cosmic timelines. To understand why this matters, imagine you're trying to determine when a marathon began by measuring how fast the runners are moving and how far they've traveled. If you measure their current speed incorrectly, your calculation of the race's start time will be wrong. Similarly, errors in measuring the cosmic expansion rate translate directly into errors in the universe's calculated age. The traditional approach to measuring the Hubble constant involves what astronomers call the distance ladder, a series of increasingly sophisticated techniques for measuring cosmic distances. The process begins with nearby stars whose distances can be determined through parallax, the apparent shift in their positions as Earth orbits the Sun. These nearby stellar distances calibrate the brightness of Cepheid variable stars, pulsating giants whose intrinsic luminosity correlates with their pulsation period. Cepheids, in turn, can be observed in galaxies millions of light years away, providing distance measurements to these stellar systems. But for the most distant galaxies needed to measure cosmic expansion, even Cepheids become too faint to observe individually. This is where type ER supernovae enter the picture. Stellar explosions so bright they can be seen across billions of light years and serve as the final rung on the cosmic distance ladder. The beauty of type Ia supernovae lies in their remarkable consistency. These thermonuclear explosions occur when white dwarf stars accrete matter from companion stars until they reach a critical mass and detonate. Because the trigger mass is always the same, roughly 1.4 solar masses, these explosions reach similar peak brightnesses. This makes them excellent standard candles for measuring cosmic distances. By observing type Ia supernovae in distant galaxies and measuring both their apparent brightness and their redshift, astronomers can determine how far away these galaxies are and how fast they're moving away from us. Plotting recession velocity against distance yields the Hubble constant. This method, refined over decades of observations, consistently produces values around 73 kilometers per second per megaparsec. But there's another way to measure the Hubble constant, one that doesn't rely on the complex distance ladder at all. This approach uses the cosmic microwave background, that ancient radiation left over from the Big Bang that we discussed earlier. The CMB provides a snapshot of the universe when it was only 380,000 years old, frozen in time like a cosmic fossil. The temperature fluctuations in the CMB contain a wealth of information about the early universe's properties, including its expansion rate, matter density, and geometric curvature. By analyzing these patterns using our best theories of cosmic evolution, cosmologists can predict what the Hubble constant should be today, roughly 13.8 billion years after the Big Bang. This prediction, based on the standard lambda cold dark matter model of cosmology, yields a Hubble constant of approximately 67 kilometers per second per megaparsec. The difference between 67 and 73 might seem small, but in cosmic terms, it's enormous. This 6-unit discrepancy corresponds to a difference of nearly 1 billion years in the calculated age of the universe. If the supernova measurements are correct, and the Hubble constant is 73, then the universe is about 12.8 billion years old. But if the CMB analysis is right and the constant is 67, the universe is 13.8 billion years old. This 1 billion year uncertainty might not seem significant compared to the vast age of the cosmos, but it's large enough to create serious problems for our understanding of stellar evolution, galaxy formation, and cosmic structure development. The tension has only grown more acute as measurements have improved. The Hubble Space Telescope, with its exceptional resolution and stability, has enabled increasingly precise measurements of Cepheid variables and supernovae. Meanwhile, space missions like Planck have mapped the cosmic microwave background with unprecedented detail. Both approaches have reduced their uncertainties, but instead of converging on the same answer, they've moved further apart. Adam Rees of Johns Hopkins University, who shared the Nobel Prize for discovering cosmic acceleration, has led efforts to refine the distance ladder approach. His team's measurements using Hubble data consistently yield Hubble constants around 74 kilometers per second per megaparsec, with uncertainties of less than 2%. These are remarkably precise measurements by astronomical standards, yet they disagree significantly with CMB predictions. The Planck satellite collaboration, analyzing cosmic microwave background data, arrives at equally precise but different conclusions. Their analysis of temperature and polarization fluctuations in the ancient radiation yields a Hubble constant of 67.4 kilometers per second per megaparsec, with similar uncertainties. The two approaches now disagree by more than 4 standard deviations, far beyond what could be explained by statistical fluctuations. This level of disagreement suggests that something fundamental is wrong with either our measurement techniques or our understanding of cosmic evolution. Perhaps the distance ladder contains systematic errors that haven't been identified despite decades of refinement. Or maybe our interpretation of the cosmic microwave background is flawed, missing crucial physics that affects the expansion history. Several potential sources of systematic error have been investigated. The calibration of Cepheid period luminosity relationships might be affected by metallicity, the abundance of heavy elements in these stars. Dust extinction could dim distant supernovae in ways that aren't fully accounted for. Gravitational lensing by intervening matter might magnify or demagnify the apparent brightness of background objects. But despite intensive scrutiny, no smoking gun has been found. Independent measurements using different techniques have largely confirmed the distance ladder results. Observations of surface brightness fluctuations in galaxies, gravitational lensing time delays, and even the tip of the red giant branch all point toward higher Hubble constant values, closer to 73 than 67. The tension has led some cosmologists to propose that the problem lies not with measurement techniques, but with our fundamental understanding of cosmic evolution. Perhaps the universe's expansion history was more complex than the standard model assumes. If the expansion rate changed in unexpected ways between the CMB epoch and today, it could reconcile the conflicting measurements. One possibility involves modifications to dark energy, the mysterious force driving cosmic acceleration. Standard cosmology assumes that dark energy behaves like a cosmological constant, maintaining constant density as the universe expands. But if dark energy evolved over time, becoming stronger or weaker, it could alter the expansion history in ways that affect Hubble constant measurements. Another possibility involves early dark energy, a hypothetical component that was significant in the universe's youth but became negligible later. Such a component could affect the sound horizon imprinted in the cosmic microwave background while having minimal impact on more recent cosmic evolution. This could reconcile CMB predictions with distance ladder measurements. Some researchers have proposed modifications to the standard model involving additional relativistic particles, often called dark radiation. These particles would have been important in the early universe, affecting the expansion rate during the CMB epoch. Their presence could alter the relationship between early and late universe expansion in ways that resolve the Hubble tension. More exotic proposals involve modifications to gravity itself. Perhaps Einstein's general relativity, while extraordinarily successful in most contexts, breaks down on cosmic scales or at certain epochs. Modified gravity theories could potentially alter cosmic expansion in ways that reconcile the conflicting measurements, though such modifications must be carefully crafted to avoid contradicting other observational evidence. The stakes involved in resolving the Hubble tension extend far beyond academic curiosity. The Hubble constant affects calculations of cosmic age, the timeline for structure formation, and predictions for the universe's ultimate fate. If the higher distance ladder value is correct, it implies the universe expanded faster than expected, potentially affecting our understanding of when the first stars formed, when galaxies assembled, and when complex structures emerged. A younger universe, implied by a higher Hubble constant, would compress the timeline for cosmic evolution. Galaxies would have had less time to form and grow, potentially explaining some of the surprisingly mature early galaxies observed by the James Webb Space Telescope. But it would also create problems for stellar evolution models, which suggest that the older stars require more time to evolve than a younger universe would provide. The resolution of the Hubble tension may require breakthrough observations or revolutionary theoretical insights. Future space telescopes with even greater precision might identify systematic errors in current measurements or provide entirely new ways to measure cosmic expansion. Alternatively, theoretical advances might reveal new physics that naturally explains the discrepancy. The tension serves as a reminder that cosmology, despite its remarkable successes, remains an evolving science. Our understanding of the universe's expansion history, based on observations spanning less than a century, may still contain fundamental gaps. The cosmic clock that seems so precisely calibrated may actually be keeping time according to rules we haven't fully deciphered. As astronomers continue to refine their measurements and theorists explore new models, the Hubble tension stands as one of the most important unsolved problems in cosmology. Its resolution could reveal new physics, force revisions to fundamental theories, or simply require more careful accounting of subtle systematic effects. Whatever the answer, it will likely transform our understanding of cosmic time and the universe's expansion history. The disagreement between these cosmic timekeepers suggests that the universe may be more mysterious than we imagined, with expansion properties that don't fit neatly into our current theoretical framework. Adjusting this cosmic clock could indeed change everything we think we know about the age and evolution of the cosmos. In 1998, two teams of astronomers made a discovery so shocking that it overturned decades of cosmological thinking and eventually earned them the Nobel Prize. They were studying distant supernovae, expecting to measure how much the universe's expansion was slowing down due to gravity. Instead, they found something that defied all expectations. The expansion of the universe was actually speeding up. This acceleration implied the existence of something completely unexpected, a repulsive force that pervades all of space and grows stronger as the universe expands. Scientists called this mysterious component dark energy, and it now appears to constitute roughly 70% of everything that exists. Yet we have no idea what dark energy actually is, how it works, or most importantly for our story, whether it has remained constant throughout cosmic history. The discovery of dark energy fundamentally changed our understanding of cosmic time. If the universe's expansion has been accelerating for billions of years, then simple calculations based on constant expansion rates would underestimate the universe's age. The cosmos would have expanded more slowly in the past than present-day measurements suggest, meaning it took longer to reach its current size than astronomers initially thought. But dark energy's role in cosmic chronology extends far beyond this basic correction. If dark energy itself has evolved over time, becoming stronger or weaker at different epochs, it could dramatically alter our understanding of when cosmic events occurred. The universe's age would become not just a single number, but a complex function of how this mysterious force has behaved throughout cosmic history. To understand why dark energy matters so much for cosmic time, we need to explore what it actually does to the fabric of space itself. Unlike matter, which becomes more dilute as the universe expands, dark energy maintains constant density even as space stretches. As the universe grows larger, there's more space and therefore more dark energy. This creates a runaway effect where dark energy becomes increasingly dominant over time. Think of blowing up a balloon that's painted with dots representing galaxies. As the balloon expands, the dots move apart, but if you could somehow add more balloon material between the dots as you inflated it, the expansion would accelerate. That's essentially what dark energy does to space. It fills in the expanding volume with more repulsive force, causing the expansion to speed up rather than slow down. The simplest model of dark energy assumes it behaves like Einstein's cosmological constant, the mathematical term he introduced to balance gravity in a static universe. In this scenario, dark energy has remained perfectly constant throughout cosmic history, never changing in strength or properties. This model, called lambda CDM, forms the foundation of modern cosmology and successfully explains many observations. But the cosmological constant raises profound questions about the nature of space and time. Quantum field theory predicts that empty space should be seething with virtual particles that pop in and out of existence, creating what physicists call vacuum energy. When calculated, this vacuum energy density comes out to be 10 to the power of 120 times larger than the observed dark energy density, the worst prediction in the history of physics. This enormous discrepancy suggests that either our understanding of quantum mechanics is fundamentally flawed, or that some unknown mechanism cancels out most of the vacuum energy, leaving only the tiny residue we observe as dark energy. Neither possibility is particularly satisfying, and both leave open the question of whether dark energy has remained constant over cosmic time. If dark energy has evolved throughout the universe's history, it would profoundly affect our age calculations. During the matter-dominated era, when galaxies and stars were forming, dark energy might have been much weaker than today. This would mean the universe expanded more slowly in the past than current models assume, requiring additional time to reach its present state. Alternatively, dark energy might have been stronger in the early universe, perhaps playing a role in cosmic inflation, the hypothetical period of exponential expansion that occurred in the first fraction of a second after the Big Bang. If early dark energy dominated the expansion during critical epochs of cosmic evolution, it could explain why galaxies and large-scale structures appear more mature than expected in distant observations. Several theoretical models propose dynamic dark energy that changes over time. Quintessence models suggest that dark energy behaves like a slowly rolling scalar field, similar to the field thought to drive cosmic inflation, but evolving much more gradually. The strength of quintessence could vary over billions of years, sometimes accelerating expansion more strongly, sometimes more weakly. Phantom dark energy represents an even more exotic possibility. In phantom models, dark energy grows stronger over time, eventually overwhelming all other forces in the universe. This leads to a scenario called the Big Rip, where accelerating expansion eventually tears apart galaxies, stars, atoms, and even space-time itself. While observational evidence doesn't currently support phantom behavior, the possibility remains open. K-essence models propose that dark energy depends not just on the value of an underlying field, but also on how rapidly that field changes. This creates more complex evolutionary histories where dark energy could strengthen and weaken in cycles, or transition abruptly between different phases. Such behavior could create multiple epochs with different expansion rates, complicating age calculations. The observational evidence for dark energy evolution remains inconclusive. Current measurements can accommodate either constant or slowly evolving dark energy. The equation of state parameter, which describes how dark energy pressure relates to its density, appears to be close to -1, the value expected for a cosmological constant. But the uncertainties are large enough to permit significant evolution. Supernovae observations, which originally revealed cosmic acceleration, provide the most direct probe of dark energy's history. By measuring the brightness and redshift of exploding stars at different cosmic epochs, astronomers can reconstruct how the expansion rate has changed over time. More distant supernovae probe earlier epochs when dark energy was less dominant, while nearby explosions sample more recent cosmic history. The Hubble Space Telescope has observed hundreds of supernovae spanning a wide range of cosmic time, from relatively nearby explosions that occurred when the universe was already mature to distant ones that exploded when it was less than half its current age. These observations trace the transition from deceleration to acceleration, pinpointing when dark energy began to dominate over matter. But supernovae alone cannot definitively determine whether dark energy has evolved. The measurements are consistent with a constant cosmological constant, but they also permit slow evolution within the observational uncertainties. More precise measurements and larger samples will be needed to detect subtle changes in dark energy's strength over cosmic time. The cosmic microwave background provides another window into dark energy's history, though it primarily constrains conditions in the very early universe. If dark energy was significant during the CMB epoch, it would affect the sound waves propagating through the primordial plasma, altering the temperature fluctuations we observe today. Current CMB measurements suggest dark energy was negligible when the universe was only 380,000 years old, at least in models where it behaves like a cosmological constant. But more complex dark energy scenarios could have left subtle imprints in the CMB that haven't yet been detected. Future measurements with higher precision might reveal these signatures. Baryon acoustic oscillations, the fossilized sound waves from the early universe, provide another probe of cosmic expansion history. These features appear as subtle clustering patterns in the distribution of galaxies, creating a standard ruler that astronomers can use to measure distances at different cosmic epochs. By tracing how this ruler appears to change size with redshift, cosmologists can reconstruct the expansion history and test for dark energy evolution. Large galaxy surveys have mapped millions of cosmic objects, measuring their positions and redshifts to create three-dimensional maps of cosmic structure. The Sloan Digital Sky Survey, the Dark Energy Survey, and other ambitious projects have traced baryon acoustic oscillations across billions of years of cosmic history. These measurements generally support constant dark energy, but with uncertainties that still permit evolution. Gravitational lensing offers yet another approach to studying dark energy's history. When light from distant galaxies passes through regions of space with different matter densities, it gets bent by gravity, creating distorted images. The amount of distortion depends on both the matter distribution and the cosmic expansion rate when the light was traveling. Weak lensing surveys measure tiny distortions in the shapes of millions of galaxies. Using statistical analysis, to map the distribution of both visible and dark matter throughout the universe. Because lensing effects depend on the entire history of cosmic expansion along the light's path, they can potentially detect dark energy evolution over long periods. The interplay between dark energy and cosmic structure formation adds another layer of complexity to age calculations. Dark energy not only affects the overall expansion rate, but also influences how matter can clump together under gravity. Stronger dark energy would inhibit structure formation by stretching space more rapidly, preventing matter from accumulating into galaxies and clusters. If dark energy was weaker in the past, it would have allowed structures to form more efficiently in the early universe. This could help explain the mature galaxies observed at high redshift by the James Webb Space Telescope, which appear to have assembled faster than current models predict. A period of reduced dark energy could have provided the extra time needed for these complex systems to develop. Conversely, if dark energy was stronger in certain epochs, it could have suppressed structure formation during critical periods, affecting when the first stars ignited, when galaxies merged, and when large-scale cosmic architecture emerged. The timing of these events directly influences our interpretation of astronomical observations and our understanding of cosmic chronology. The relationship between dark energy and cosmic time becomes even more intricate when we consider quantum effects. Some theories suggest that dark energy could interact with other fundamental fields, creating feedback loops that affect its evolution. Virtual particles in the quantum vacuum might respond to changes in space-time curvature, potentially causing dark energy to evolve in response to the universe's own expansion. Anthropic reasoning adds yet another perspective to dark energy's role in cosmic time. If dark energy's strength determines whether universes can form complex structures like galaxies and stars, then we might naturally find ourselves in a universe where dark energy happened to have just the right properties to allow our existence. This could explain both dark energy's apparent fine-tuning and potentially its evolutionary history. The search for dark energy evolution continues to drive innovative observational projects. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will conduct unprecedented surveys of supernovae and galaxy clustering. The Large Synoptic Survey Telescope will map billions of galaxies and track their properties over time. The European Space Agency's Euclid mission will measure cosmic distances with extraordinary precision. These future observations may finally determine whether dark energy has remained constant or evolved throughout cosmic history. If evolution is detected, it would revolutionize our understanding of fundamental physics and force major revisions to cosmic chronology. The universe's age would become not a single number, but a complex story of how space, time, and energy have interacted over billions of years. The implications extend beyond cosmology into particle physics and quantum gravity. Understanding dark energy's nature and evolution could provide crucial clues about the fundamental structure of space-time itself. It might reveal connections between gravity and quantum mechanics that have eluded physicists for decades. As we push beyond the standard cosmological model, dark energy emerges as perhaps the greatest mystery in our quest to understand cosmic time. This invisible force, which dominates the universe's energy budget, holds the key to determining not just how fast the cosmos is expanding today, but how that expansion has changed throughout the entire history of space and time. The universe's true age may depend on secrets that dark energy has yet to reveal. What if everything we think we know about the universe's beginning is wrong? What if the Big Bang wasn't actually the start of everything, but merely one event in an infinite cosmic cycle? What if space and time have no beginning at all, stretching endlessly into the past and future? These aren't just philosophical musings, they're serious scientific alternatives to the standard Big Bang model that have been proposed, debated, and tested over decades of cosmological research. While the Big Bang theory has achieved remarkable success in explaining observations from cosmic microwave background radiation to light element abundances, it's not the only game in town. Alternative cosmological models offer radically different perspectives on cosmic time, some eliminating the concept of a universal age entirely, others suggesting the universe might be far older than 13.8 billion years. The most famous alternative to Big Bang cosmology was the steady-state theory, proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. This elegant model suggested that the universe has always looked essentially the same, with no beginning and no end. As galaxies move apart due to cosmic expansion, new matter continuously appears in the space between them, maintaining constant density throughout all of cosmic history. In the steady-state universe, there would be no cosmic age in the conventional sense. The universe would be infinitely old, having always existed in roughly its current form. Galaxies would form, evolve, and eventually disperse, but they would be constantly replaced by new ones forming from the continuously created matter. The large-scale appearance of the cosmos would remain unchanged over infinite time. Fred Hoyle, the theory's most passionate advocate, coined the term Big Bang in a somewhat derogatory attempt to ridicule the competing theory. He found the idea of a cosmic beginning philosophically unsatisfying, preferring the steady-state's eternal, self-renewing universe. Hoyle argued that the Big Bang required a moment of creation that was fundamentally unscientific, while steady-state theory needed only the continuous creation of matter at an almost undetectable rate. The rate of matter creation required by steady-state theory was extraordinarily small, roughly 1 hydrogen atom per cubic meter of space every billion years. This rate was so low that it would be virtually impossible to detect directly, yet it would be sufficient to maintain constant density as the universe expanded. Hoyle calculated that this continuous creation was no more miraculous than the sudden creation of all matter at once in the Big Bang. The steady-state model made specific, testable predictions. Since new galaxies would be forming continuously, there should be no evolution in the overall properties of the galaxy population over cosmic time. The universe should look the same, whether we observe nearby regions or distant ones. Radio surveys should reveal similar numbers and types of active galaxies at all epochs. But observations increasingly contradicted these predictions. Radio telescopes in the 1950s and 60s revealed that distant radio sources were more numerous and more powerful than nearby ones, suggesting the universe had indeed evolved over cosmic time. The discovery of quasars, extremely luminous objects that appeared only at large distances, provided further evidence that the early universe was different from today's cosmos. The final blow to steady-state theory came with the discovery of the cosmic microwave background in 1965. This ancient radiation, predicted by Big Bang theorists but completely unexpected in steady-state models, provided overwhelming evidence for a hot, dense, early phase in cosmic history. The steady-state theory gradually faded from mainstream cosmology, though it retained some supporters who proposed modified versions to account for the new observations. Despite its ultimate failure, the steady-state theory demonstrated that alternative cosmologies could make specific predictions and be tested against observations. It also raised important questions about the nature of cosmic time that continue to influence cosmological thinking. If the universe could theoretically be eternal in steady-state models, might there be other ways to avoid the problematic concept of a cosmic beginning? One such alternative emerged in the form of cyclic cosmological models, which propose that the universe undergoes endless cycles of expansion and contraction. In these scenarios, our current expanding phase would eventually reverse, causing all matter to collapse back into a dense state similar to the Big Bang. This collapse would then trigger another expansion, creating an eternal rhythm of cosmic death and rebirth. The original cyclic model, proposed in the 1930s, faced serious theoretical problems. During each contraction phase, entropy would increase, making each successive cycle slightly different from the last. Eventually, the cycles would become so distorted that the model would break down. Additionally, quantum effects during the collapse phase seemed likely to create irregularities that would prevent smooth cycling. Modern versions of cyclic cosmology have attempted to address these problems using concepts from string theory and higher dimensional physics. The ekpyrotic scenario, developed by Neil Turok, Paul Steinhardt, and others, suggests that our universe might be a three-dimensional membrane floating in higher dimensional space. Collisions between such branes could trigger Big Bang-like events, creating cycles of cosmic evolution. In ekpyrotic models, each cycle could last trillions of years, far longer than the current age of our universe. The expansion phase we're experiencing now would represent just a tiny fraction of one complete cycle. From this perspective, our 13.8 billion year timeline would be merely the latest chapter in an infinitely long cosmic story. The bouncing universe represents another approach to cyclic cosmology. Instead of complete collapse and recreation, these models suggest that the universe contracts until quantum effects or modified gravity prevents further compression, causing it to bounce back into expansion. Each bounce would launch a new era of cosmic evolution, potentially lasting much longer than our current Big Bang timeline suggests. Loop quantum cosmology, derived from attempts to quantize Einstein's general relativity, naturally produces bouncing behavior. In this framework, the repulsive effects of quantum geometry prevent the formation of true singularities, causing contracting universes to bounce back into expansion. The universe would have no beginning or end, just an infinite series of bounces stretching infinitely into the past and future. These quantum bounces could resolve many puzzles of standard Big Bang cosmology. The horizon problem, which questions why distant regions of the universe have similar temperatures despite never being in causal contact, could be explained if they were in contact during a previous cycle. The flatness problem, concerning why the universe's geometry is so close to perfectly flat, might be solved if previous cycles naturally drove the geometry toward flatness. Another class of alternative cosmologies involves the tired light hypothesis, originally proposed by Fritz Zwicky in 1929. Instead of interpreting galactic redshifts as evidence for cosmic expansion, tired light models suggest that photons lose energy as they travel through space, becoming redder over long distances. This energy loss could be caused by interactions with intergalactic matter, quantum vacuum fluctuations, or other unknown physical processes. If light truly becomes tired during its journey, then distant galaxies aren't actually receding from us. They're just appearing redshifted due to photon energy loss. This would eliminate the need for cosmic expansion entirely, suggesting that the universe might be static and potentially infinitely old. The apparent expansion would be an illusion created by our misinterpretation of redshift observations. However, tired light models face severe observational difficulties. They predict that distant objects should appear blurred due to the scattering processes that cause energy loss. But observations show that distant galaxies appear just as sharp as nearby ones. Tired light also struggles to explain the cosmic microwave background, time dilation effects in distant supernovae, and the observed abundances of light elements. Despite these problems, some researchers continue to explore tired light mechanisms. Plasma physics effects, interactions with dark matter, or modifications to photon behavior in curved space-time might potentially cause redshift without cosmic expansion. These investigations remain highly speculative, but serve as useful tests of our understanding of fundamental physics. Variable speed of light cosmologies represent yet another alternative approach. These models suggest that fundamental constants like the speed of light might have changed over cosmic history. If light traveled faster in the early universe, it could have had more time to establish thermal equilibrium across vast distances, solving the horizon problem without requiring cosmic inflation. In variable speed of light models, the universe could be much older than conventional calculations suggest. If light moved faster when it was emitted from distant galaxies, then those galaxies could be much further away and much older than their redshifts indicate. The timeline of cosmic evolution would need to be completely reconsidered, potentially allowing far more time for structure formation and stellar evolution. Mirror matter cosmologies propose that our universe might contain a hidden sector of particles that interact only weakly with ordinary matter. These mirror particles would have their own complex chemistry and could form mirror stars, mirror planets, and mirror galaxies. The gravitational effects of mirror matter could influence cosmic expansion without being directly observable, potentially altering age calculations. If mirror matter contributed significantly to the universe's energy density, it could affect the expansion history in ways that haven't been accounted for in standard models. The universe might have expanded differently than we assume, requiring adjustments to age estimates. Mirror matter could also provide alternative explanations for dark matter and dark energy, fundamentally changing our understanding of cosmic composition. Brain-world cosmologies, inspired by string theory, suggest that our four-dimensional spacetime might be embedded in higher dimensional space. The properties of these extra dimensions could influence cosmic expansion, gravity, and the fundamental constants that govern physical processes. Our universe might be just one of many brains floating in a higher dimensional bulk space. In some brain world scenarios, the apparent Big Bang could represent the moment when our brain separated from another brain or began interacting with bulk space in a new way. The universe might have existed in different forms before this event, potentially for infinite time. The Big Bang would mark a transition rather than a true beginning, making the universe far older than conventional estimates suggest. These alternative cosmologies demonstrate that the concept of cosmic age is far more flexible than it might initially appear. While the Big Bang model currently provides the best explanation for most observations, it's important to remember that scientific theories evolve as new evidence emerges. The universe might indeed be older than we think, or the very concept of cosmic age might need to be reconsidered entirely. The exploration of alternative cosmologies serves multiple purposes in scientific research. It tests the robustness of the standard model by challenging its assumptions and predictions. It provides frameworks for understanding observations that don't fit conventional explanations. And it reminds us that our current understanding of cosmic time and space might be incomplete. As observational capabilities continue to improve, alternative cosmologies face increasingly stringent tests. The James Webb Space Telescope, gravitational wave detectors, and other advanced instruments provide new ways to probe the fundamental nature of space, time, and cosmic evolution. These observations might confirm the standard Big Bang timeline, or they might reveal evidence for alternative scenarios that dramatically alter our understanding of cosmic age. The lesson from studying alternative cosmologies is that cosmic time itself is a more complex and uncertain concept than we might assume. The universe's age depends critically on our understanding of fundamental physics, and changes to that understanding could significantly alter our cosmic timeline. These models show that age is not always fixed, and that the universe might have been keeping time according to rules we haven't yet discovered. At the very edge of space and time, where the universe shrinks to unimaginably small scales and temperatures soar beyond anything we can comprehend, the familiar laws of physics begin to break down. This is the realm of quantum gravity, where Einstein's smooth curved space-time meets the bizarre probabilistic world of quantum mechanics. Here, at the Planck scale, space and time themselves might become granular, discontinuous, and subject to the strange rules that govern the quantum world. Understanding what happens in this extreme regime could revolutionize our conception of cosmic time itself. If space-time is fundamentally quantum mechanical, then the very notion of a beginning to the universe, the Big Bang singularity that marks time equals zero in our current models, might be an illusion. The universe might have no true beginning at all, stretching infinitely into the past in ways that classical physics cannot describe. The journey into quantum gravity begins with recognizing the fundamental incompatibility between our two most successful theories of physics. General relativity describes gravity as the curvature of smooth, continuous space-time, while quantum mechanics reveals that energy, momentum, and other physical quantities come in discrete packets called quanta. At everyday scales, these theories operate in separate domains and work perfectly well independently. But in the extreme conditions of the very early universe, both theories must apply simultaneously. When the universe was smaller than the Planck length, roughly 10 to the power of -35 meters, and younger than the Planck time, about 10 to the power of -43 seconds, quantum effects would have dominated the structure of space-time itself. At these scales, the smooth geometry of Einstein's relativity would dissolve into a foaming, fluctuating quantum landscape. The Planck scale represents the fundamental limit of our current physical theories. Named after Max Planck, the pioneer of quantum theory, these units are constructed from the most basic constants of nature, the speed of light, Newton's gravitational constant, and Planck's constant. They represent the natural scales at which quantum gravitational effects become important, beyond which our current understanding breaks down completely. At the Planck length, space-time itself would no longer be smooth, but would instead resemble a turbulent sea of quantum fluctuations. Virtual particles would pop in and out of existence, creating and destroying tiny wormholes, causing the fabric of reality to writhe and churn at scales far below anything we can observe. Time itself might become discontinuous, proceeding in discrete quantum jumps, rather than the smooth flow we experience at larger scales. This quantum foam, as physicists call it, could fundamentally alter our understanding of cosmic origins. If space and time are quantized at the smallest scales, then the Big Bang singularity, where all known physics breaks down, might not represent a true beginning. Instead, it could mark the transition from a quantum gravitational epoch that we don't yet understand to the classical regime where general relativity takes over. Loop quantum gravity, one of the leading approaches to quantum gravity, suggests that space itself is made of discrete building blocks, tiny loops of gravitational field lines that form the fundamental fabric of reality. In this picture, space is not infinitely divisible, but has a minimum size, the Planck length. Time too might be quantized, progressing in discrete steps rather than continuously. When applied to cosmology, loop quantum gravity produces a remarkable result. The crushing gravitational forces that create the Big Bang singularity in classical relativity are overcome by quantum repulsion when matter reaches the Planck density. Instead of infinite compression, the universe bounces, transitioning from a previous contracting phase to the expanding phase we observe today. This quantum bounce eliminates the need for a cosmic beginning entirely. The universe could be infinitely old, undergoing endless cycles of contraction and expansion, each bounce lasting for periods that dwarf our current 13.8 billion year timeline. Our observable universe would represent just one expansion phase in an eternal cosmic rhythm stretching infinitely into the past and future. The pre-bounce universe, according to loop quantum cosmology, could have been vastly different from our current cosmos. It might have been contracting for trillions upon trillions of years before reaching the critical density where quantum effects triggered the bounce. During this long contraction phase, complex structures could have evolved, been compressed to near infinite density, then re-expanded in the bounce that created our current expanding universe. String theory, the other major approach to quantum gravity, offers a different perspective on cosmic origins. In string theory, the fundamental constituents of reality are not point-like particles, but tiny vibrating strings, existing in multiple dimensions beyond the three of space and one of time that we directly experience. These extra dimensions could provide new ways for the universe to evolve that classical physics cannot describe. One of the most intriguing implications of string theory is that what we interpret as the Big Bang might actually be a collision between higher dimensional objects called branes. Our universe could be a three-dimensional membrane floating in higher dimensional space, and cosmic expansion could result from the aftermath of collisions with other branes. In brane collision scenarios, the age of our universe would refer only to the time since the last collision, not to the age of the branes themselves. The branes could have existed for infinite time, occasionally colliding and creating new phases of cosmic evolution. Our Big Bang would mark just one such collision in an eternal sequence stretching infinitely into the past. String theory also suggests the possibility of pre-Big Bang scenarios where the universe existed in a fundamentally different phase before the hot, dense state we identify with cosmic origins. The pre-Big Bang universe might have been in a state of contraction, with completely different physical laws governing its evolution. The transition to our current expanding phase could have occurred through mechanisms involving higher dimensional physics. These pre-Big Bang models often involve concepts like T-duality, a mathematical relationship in string theory that connects small and large distance scales. In some scenarios, a contracting universe with very small dimensions could be mathematically equivalent to an expanding universe with large dimensions. The Big Bang would represent the transition point between these dual descriptions, not necessarily a true beginning. Causal set theory proposes yet another approach to quantum gravity, suggesting that space-time emerges from a more fundamental discrete structure. In this framework, space-time points are connected by causal relationships, creating a network that gives rise to the familiar four-dimensional geometry we observe. The universe would be fundamentally digital at the smallest scales, with space-time built from discrete events rather than continuous fields. If causal set theory is correct, then time itself would be quantized, proceeding in discrete steps determined by the fundamental causal structure. The concept of cosmic age would need to be reconsidered in terms of the number of discrete time steps, since some arbitrary starting point rather than continuous duration measured by clocks. Emergent gravity theories suggest that gravity itself might not be fundamental, but could arise from more basic quantum mechanical processes, similar to how temperature emerges from molecular motion. In these scenarios, space-time and gravity would be collective phenomena that appear only at large scales, while the underlying reality would be governed by quantum information and entanglement. Eric Verlinder's entropic gravity proposal suggests that gravitational attraction results from changes in entropy, the measure of disorder in a system. If gravity emerges from quantum information, then the early universe, when quantum effects dominated, might have evolved according to completely different principles than those we observe today. The apparent beginning of time might reflect the emergence of classical space-time from a more fundamental quantum information substrate. Holographic theories inspired by black hole physics suggest that all the information in a volume of space can be encoded on its boundary, like a hologram. Applied to cosmology, this implies that our three-dimensional universe might actually be the holographic projection of information encoded on a two-dimensional surface. The universe's age and evolution would then reflect the dynamics of this holographic encoding. The holographic principle has profound implications for cosmic time. If the universe is fundamentally two-dimensional, with the third dimension and time emerging as effective descriptions, then questions about cosmic age become questions about the evolution of information on the holographic boundary. The universe might be far older, younger, or exist in a completely different temporal framework than our three-dimensional perspective suggests. Quantum cosmology attempts to apply quantum mechanics directly to the universe as a whole, treating the entire cosmos as a quantum system subject to the probabilistic laws that govern atomic and subatomic particles. In this approach, The universe doesn't have a definite age or beginning, but exists in a superposition of different possible histories, each with its own timeline and evolutionary path. The Wheeler-DeWitt equation, sometimes called the Schrödinger equation for the universe, describes how these quantum cosmological states evolve. Solutions to this equation can include universes that tunnel into existence from nothing, emerge from quantum fluctuations, or exist in eternal superpositions of different ages and configurations. Hartley-Hawking. No boundary proposal suggests that the universe has no boundary in space or time, similar to how Earth's surface has no edge despite being finite. In this model, time becomes space like in the extreme early universe, and the question of what came before the Big Bang becomes as meaningless as asking what's north of the North Pole. The no boundary condition eliminates the need for initial conditions entirely. The universe would be completely self-contained, with no beginning or end and no need for external creation. Time would emerge naturally from the quantum geometry, and the apparent age of the universe would reflect the evolution of this emergent time rather than duration since a definite beginning. These quantum gravitational approaches to cosmology share a common theme. They all suggest that our conventional understanding of cosmic time and age might be fundamentally incomplete. Whether through quantum bounces, brain collisions, emergent spacetime, or quantum superpositions, the universe might be far more temporally complex than the simple Big Bang timeline suggests. The implications extend beyond abstract theoretical physics. If the universe underwent quantum gravitational evolution before the classical Big Bang epoch, it could have had vast amounts of time to develop complex structures, solve cosmological puzzles like horizon and flatness problems, and set up the initial conditions for classical cosmological evolution. Experimental tests of quantum gravity remain extremely challenging due to the enormous energies required to probe Planck-scale physics directly. However, cosmological observations might preserve subtle imprints of quantum gravitational effects from the early universe. The cosmic microwave background, gravitational waves from the Big Bang, and observations of primordial black holes could potentially reveal signatures of quantum spacetime. Future gravitational wave detectors might be sensitive enough to detect primordial gravitational waves produced during quantum gravitational epochs. These waves would carry information about the structure of spacetime at the Planck scale, providing our first direct evidence of quantum gravity effects in cosmology. The Large Hadron Collider and future particle accelerators might probe energies high enough to reveal extra dimensions or other signatures of string theory. While far from Planck-scale energies, these experiments could provide crucial tests of the theoretical frameworks that predict quantum gravitational effects in cosmology. As our understanding of quantum gravity develops, it may reveal that the universe has no single age at all. Instead, cosmic time might be a complex, multifaceted concept that depends on which quantum gravitational processes dominate at different scales and epochs. The 13.8 billion year timeline that seems so definitive might represent just one layer of a far more intricate temporal structure. The marriage of quantum mechanics and gravity promises to revolutionize our understanding of cosmic origins, evolution, and ultimate fate. In this quantum gravitational universe, time itself might be more mysterious and malleable than we ever imagined, stretching the story of cosmic evolution far beyond our current Big Bang-centered timeline into realms that classical physics cannot even describe. Maybe the universe has no single age at all, but exists in a quantum superposition of different temporal histories, each carrying its own story of cosmic evolution across scales and epochs that dwarf our conventional understanding of space and time. Imagine you're standing in a vast library containing every book ever written, but there's a catch. The farther you walk from your starting position, the dimmer the lights become, until eventually you reach a wall of impenetrable darkness beyond which no books can be read. This is essentially the situation astronomers face when trying to observe the distant universe. There are fundamental limits to how far we can see, how far back in time we can probe, and how much information we can extract from the ancient light that reaches our telescopes. These observational boundaries aren't just technical limitations that better instruments might overcome. Some represent absolute physical barriers built into the structure of space-time itself. Understanding these limits is crucial for interpreting what telescopes reveal about cosmic age and evolution, because what we can't see might be just as important as what we can observe. The most fundamental barrier to cosmic observation is the finite speed of light combined with the finite age of the universe. Even if the universe is infinitely large, we can only observe regions whose light has had enough time to reach us since the Big Bang. This creates what cosmologists call the observable universe, a sphere centered on Earth with a radius equal to the distance light could have traveled in 13.8 billion years. But the situation is more complex than this simple picture suggests. Because space itself has been expanding throughout cosmic history, galaxies that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light years. The edge of the observable universe, called the cosmological horizon, actually lies about 46.5 billion light years away in today's units. Beyond this horizon lies the unobservable universe, regions of space that exist but whose light hasn't had time to reach us yet. If the universe is infinite, as many models suggest, then the unobservable portion would be infinitely larger than what we can see. We're essentially peering at cosmic history through a keyhole, seeing only a tiny fraction of what might exist. This observational limit has profound implications for understanding cosmic age. If the universe extends far beyond our horizon, it might contain regions with completely different evolutionary histories, ages, and physical properties. The 13.8 billion year timeline we measure might apply only to our local cosmic neighborhood, while distant regions could tell entirely different stories about space and time. Even within the observable universe, there are fundamental barriers to how far back in time we can see. The cosmic microwave background represents an almost impenetrable wall in our observations, marking the epoch when the universe first became transparent to light. Before this moment, when the cosmos was only 380,000 years old, it was opaque to electromagnetic radiation. This cosmic opacity creates what astronomers call the surface of last scattering. We can observe the universe at this moment with exquisite detail, mapping temperature fluctuations that reveal conditions in the primordial plasma. But we cannot see beyond this surface using ordinary telescopes. The earlier universe, from the Big Bang to recombination, remains hidden behind a veil of hot, ionized gas. Future observations might push slightly beyond this electromagnetic barrier. Gravitational waves, ripples in space-time itself, can propagate freely through the opaque early universe. Primordial gravitational waves generated during cosmic inflation or other early universe processes could carry information from the first moments after the Big Bang, potentially revealing whether the universe is older than current estimates suggest. Neutrinos provide another potential window into the hidden early universe. These ghostly particles interact so weakly with matter that they can travel virtually unimpeded from the earliest epochs. The cosmic neutrino background, predicted to exist but not yet directly detected, would contain information about conditions when the universe was only 1 second old. The practical limits of current telescopes create additional boundaries to cosmic observation. Even the most powerful instruments can only detect objects above a certain brightness threshold, and atmospheric interference, instrumental noise, and cosmic background radiation further constrain what can be observed. These technical limitations might hide crucial evidence about cosmic age and evolution. The James Webb Space Telescope represents the current pinnacle of observational capability, but it too faces fundamental limits. Its primary mirror, impressive as it is, can only collect a finite amount of light. Distant galaxies that formed when the universe was very young emit only a few photons that survive the journey to Earth. some of the most ancient cosmic structures might remain forever beyond our detection threshold. Gravitational lensing offers a way to push beyond some of these limits by using massive galaxy clusters as natural telescopes. When light from distant galaxies passes through these clusters, their gravity bends and magnifies the light, allowing us to see objects that would otherwise be too faint to detect. This technique has revealed some of the most distant galaxies ever observed, but it's limited by the random distribution of suitable lensing clusters. The resolution limits of telescopes create another observational boundary. Even with perfect instruments, there's a fundamental limit to how much detail can be resolved in distant objects due to the wave nature of light. Distant galaxies appear as mere points of light, preventing detailed studies of their internal structure and evolution. We can measure their overall properties, but miss crucial information about how they formed and evolved. Spectroscopic observations, which reveal the chemical composition and physical properties of cosmic objects, face their own limitations. Distant galaxies are so faint that obtaining detailed spectra requires enormous amounts of observing time, even with the largest telescopes. Many interesting objects remain spectroscopically unconfirmed, limiting our understanding of their nature and evolutionary state. The redshift-distance relationship, fundamental to cosmic age determinations, breaks down at extreme distances. Beyond certain redshifts, small measurement errors translate into enormous uncertainties in distance and age. The most distant galaxies, which should provide crucial information about the early universe, paradoxically become the most difficult to study precisely. Dust extinction presents yet another observational challenge. Interstellar and intergalactic dust can absorb and scatter light from distant objects, making them appear dimmer and redder than they actually are. While astronomers have developed techniques to correct for dust effects, these corrections are model-dependent and might systematically bias age estimates. The cosmic infrared background, diffuse emission from dust heated by starlight throughout cosmic history, creates a faint glow that interferes with observations of the most distant objects. This background light, while carrying valuable information about cosmic star formation history, makes it difficult to detect the faintest high redshift galaxies that might reveal the earliest epochs of cosmic evolution. Sample selection effects introduce systematic biases into cosmic age determinations. Current surveys preferentially detect the brightest, most massive galaxies at high redshift, potentially missing entire populations of smaller, fainter objects that might tell different stories about early cosmic evolution. The galaxies we can observe might not be representative of the full population that existed in the early universe. Cosmological time dilation affects how we interpret observations of distant objects. Events in the early universe appear to unfold more slowly when viewed from our current epoch due to the expansion of space. Supernovae at high redshift take longer to brighten and fade, while galaxy evolution appears slowed down. These effects must be carefully accounted for in age determinations. The finite lifetimes of different astronomical phenomena create temporal selection effects. We can only observe stars during their active lifetimes, galaxies while they're forming stars, and quasars while their central black holes are actively feeding. Objects that were active in the distant past might now be quiescent and invisible, biasing our understanding of early cosmic evolution. Future observational capabilities promise to push some of these boundaries further back in time and space. The Nancy Grace Roman Space Telescope will conduct unprecedented surveys of distant supernovae and galaxies, potentially revealing new populations of early cosmic objects. Ground-based extremely large telescopes will achieve angular resolutions previously impossible, allowing detailed studies of distant galaxy structure. Radio astronomy offers unique advantages for probing cosmic history. Radio waves can penetrate dust that blocks optical light, and radio telescopes can observe the 21-centimeter line of neutral hydrogen, potentially mapping the distribution of matter in the early universe. The square-kilometer array, currently under construction, will revolutionize our understanding of cosmic evolution through radio observations. Gravitational wave astronomy represents an entirely new window onto cosmic history. Future space-based detectors might observe mergers of primordial black holes formed in the early universe, providing direct information about conditions shortly after the Big Bang. These observations could reveal whether the universe underwent phases of evolution not captured in current models. Multi-messenger astronomy, combining observations across the electromagnetic spectrum with gravitational waves and neutrinos, promises to overcome some traditional observational limits. By observing the same cosmic events through different channels, astronomers can extract more complete information about cosmic evolution and potentially detect signatures of physics beyond current theories. Machine learning and artificial intelligence are beginning to revolutionize astronomical data analysis, potentially extracting information from noisy observations that would be missed by traditional techniques. These methods might reveal faint signals of ancient cosmic structures or identify systematic patterns that challenge current models of cosmic evolution. Despite these advancing capabilities, some observational limits may prove absolute. The cosmic microwave background will likely remain the farthest electromagnetic signal we can detect. The cosmological horizon sets a fundamental boundary to the observable universe. Quantum mechanics itself might limit how precisely we can measure certain cosmic properties. The question of whether these observational limits hide evidence for an older universe remains open. Perhaps the most ancient cosmic structures lie just beyond our current detection threshold, waiting for the next generation of instruments to reveal them. Or maybe the universe has been more complex and longer lived than our observations suggest, with crucial evidence hidden behind the various barriers that constrain cosmic observation. As we push these boundaries with increasingly sophisticated techniques, we may find that the universe has been keeping secrets about its age and evolution in the regions of space and time that remain hidden from our view. More data may indeed redefine cosmic time, revealing that the story of the universe is far longer and more complex than our current 13.8 billion year timeline suggests. The limits of observation remind us that our understanding of cosmic age is necessarily incomplete based on the finite sample of cosmic history that happens to be visible from our particular location in space and time. The full story of cosmic evolution might extend far beyond these observational boundaries into regions that will challenge our most fundamental assumptions about the nature of space, time, and cosmic history. Standing beneath a star-filled night sky, humans have always wondered about their place in the cosmic order. Are we fleeting sparks in an ancient universe, or significant players in a cosmic drama that has only just begun? The age of the universe isn't just a number, it's a fundamental parameter that shapes how we understand our existence, our origins, and our ultimate destiny. If the cosmos is older than we think, or if time itself is more complex than we imagine, the implications extend far beyond astronomy into the deepest questions of philosophy, meaning, and human significance. The discovery that the universe has a finite age was one of the most profound revelations in human history. For millennia, philosophers and theologians debated whether the world was eternal or created, but they could never resolve the question through observation alone. The Big Bang Theory changed everything by providing scientific evidence for a cosmic beginning, a moment when space, time, matter, and energy all came into existence together. This cosmic beginning carries enormous philosophical weight. If the universe started from nothing 13.8 billion years ago, it suggests that existence itself is contingent rather than necessary. Everything we see around us, from galaxies to planets to living beings, arose from initial conditions that might have been different or might never have occurred at all. The universe appears to be a cosmic accident, albeit one that led to remarkable complexity and beauty. But what if this picture is wrong? What if the universe is much older than we think, or has no beginning at all? The philosophical implications would be equally profound. An ancient or eternal cosmos would shift our perspective from seeing existence as contingent to viewing it as perhaps inevitable or necessary. We would be participants in a story that has been unfolding for far longer than we imagined, possibly forever. The question of cosmic age intersects with fundamental issues in the philosophy of time. Is time something real and objective, flowing from past to future regardless of observers? Or is it merely a subjective experience, an illusion created by consciousness as it processes information? Different answers to these questions lead to different interpretations of what cosmic age actually means. If time is objective and universal, then the universe truly has an age in some absolute sense. The 13.8 billion year timeline represents the actual duration since creation, measured by a cosmic clock that ticks independently of human observation. In this view, we're genuinely late arrivals in cosmic history, emerging when the universe was already ancient by any reasonable standard. But if time is subjective or emergent, then cosmic age becomes more complicated. Perhaps different observers, moving at different speeds or experiencing different gravitational fields, would measure different ages for the same universe. The cosmic timeline might be as much about perspective as about objective reality. What seems like 13.8 billion years to us might appear completely different to hypothetical observers in other parts of the cosmos. The concept of deep time, geological and cosmic timescales that dwarf human experience, challenges our intuitive understanding of temporal significance. Human history spans only a few thousand years, human civilization perhaps 10,000, and our species has existed for only a few 100,000 years. If the universe is 13.8 billion years old, then all of human existence represents less than 1/100% of cosmic history. This perspective can be either humbling or terrifying, depending on your philosophical disposition. Are we insignificant specks in a vast ancient cosmos? Or are we remarkable emergent phenomena that arose despite incredible odds? The answer might depend not just on the universe's age, but on how that age relates to the fundamental processes that make complexity and consciousness possible. If the universe turns out to be much older than current estimates suggest, it would extend our cosmic insignificance even further. Imagine discovering that the cosmos has been evolving for hundreds of billions or trillions of years. Human existence would shrink to an even tinier fraction of cosmic history, raising profound questions about meaning and purpose in such an ancient universe. Alternatively, an older universe might actually enhance human significance. More time would have been available for the complex processes that led to our existence. Stars would have had more opportunities to create and distribute the heavy elements essential for life. Planetary systems would have had more time to develop stable conditions suitable for biological evolution. In this view, an older universe might make our existence less miraculous, more natural. The anthropic principle, the observation that the universe seems remarkably well tuned to allow the existence of complex structures like stars, planets, and living beings, takes on different meanings depending on cosmic age. If the universe is relatively young and we arose quickly, it might suggest that the fundamental constants and laws of physics are precisely calibrated to enable complexity. This apparent fine-tuning has led some philosophers to argue for design or multiple universe scenarios. But if the universe is much older than we think, it might have had time to explore many different configurations and evolutionary pathways. What appears to be fine-tuning might actually reflect the natural outcome of prolonged cosmic evolution. Given enough time, complexity and consciousness might be inevitable rather than miraculous. The anthropic principle would shift from suggesting special cosmic conditions to simply acknowledging that observers can only exist in universes that have had sufficient time for complexity to emerge. The possibility that the universe has no beginning at all raises even more profound philosophical questions. If cosmic time extends infinitely into the past, then existence itself becomes fundamentally different from our usual understanding. Instead of a creation event that brought everything into being, we would live in a reality that has always existed in some form. Eternal universe models, whether through steady-state cosmology, cyclic evolution, or quantum gravitational scenarios, challenge many of our deepest philosophical and religious assumptions. They eliminate the need for a first cause or creator while raising new questions about the nature of existence itself. In an eternal cosmos, every possible configuration of matter and energy would eventually occur, perhaps infinitely many times. This leads to the unsettling possibility of eternal recurrence, the idea that our lives and experiences might repeat infinitely throughout cosmic history. If the universe has unlimited time to explore all possible arrangements of matter and energy, then exact duplicates of our solar system, our planet, and ourselves might exist elsewhere in space or time. The uniqueness of individual experience becomes questionable in such a scenario. The relationship between cosmic age and the emergence of consciousness represents another profound philosophical frontier. If the universe is older than we think, it raises the possibility that consciousness has emerged many times before, perhaps in forms we cannot imagine. Advanced civilizations might have risen and fallen countless times throughout cosmic history, leaving no trace detectable by our current instruments. This temporal chauvinism, the assumption that we live at a special time in cosmic history, might be as misguided as the spatial chauvinism that once placed Earth at the center of the universe. Perhaps consciousness and intelligence are common outcomes of cosmic evolution, arising whenever conditions permit and disappearing when circumstances change. We might be just the latest in an endless succession of conscious beings contemplating their place in the cosmos. The possibility of pre-existing civilizations raises profound questions about cosmic inheritance and responsibility. If intelligence has emerged many times before, might there be artifacts, messages, or modified physical constants left by previous cosmic inhabitants? The search for extraterrestrial intelligence typically focuses on contemporary signals, but an older universe might contain evidence of far more ancient technological activity. These considerations connect to broader questions about the purpose and direction of cosmic evolution. Does the universe have goals or tendencies that drive it toward greater complexity and consciousness? Or is everything we observe simply the result of random processes operating over vast timescales? An older universe would provide more opportunities for both purposeful evolution and meaningless drift. The heat-death scenario, where the universe eventually reaches maximum entropy and all interesting processes cease, takes on different character depending on cosmic age. If the universe is relatively young, we might be living during a brief special epoch when complexity and consciousness are possible. The vast majority of cosmic time would be spent in a cold, dark, empty state with no stars, planets, or living beings. But if the universe is much older or operates cyclically, the heat death might be less final than it appears. Quantum fluctuations could eventually recreate complex structures, even intelligent beings, given unlimited time. The cosmos might undergo periodic rejuvenation through unknown physical processes. What seems like an ending might actually be a transition to different phases of cosmic evolution. The measurement problem in quantum mechanics becomes particularly intriguing in the context of cosmic age and consciousness. If consciousness plays a role in quantum measurement and wave function collapse, then the emergence of observers might fundamentally alter the physics operating in the universe. An older cosmos would have had more opportunities for consciousness to emerge and potentially influence physical reality. This leads to speculative but fascinating possibilities about observer participatory cosmology. Perhaps the universe's apparent age and history depend partly on the observations and measurements made by conscious beings. Different types of observers might literally inhabit different cosmic timelines or experience different versions of cosmic history. The question of whether mathematics and physical laws are discovered or invented takes on new dimensions in an older universe. If conscious beings have been contemplating mathematical and physical truths for far longer than human history, they might have already explored all possible mathematical structures and physical theories. We might be rediscovering eternal truths that have been found countless times before. Free will and determinism also intersect with cosmic age in complex ways. If the universe has been evolving according to deterministic physical laws for vast periods, are we simply complex arrangements of particles following predetermined paths? Or does the emergence of consciousness introduce genuine novelty and choice into cosmic evolution? An older universe might have had time to explore the full implications of both deterministic and quantum mechanical processes. The meaning of death and mortality shifts dramatically depending on cosmic age and structure. In a young universe destined for heat death, individual consciousness appears to be a brief flicker in an ultimately meaningless cosmos. But in an older or cyclical universe, death might be less final. Information patterns that constitute consciousness might be recreated through natural processes or technological resurrection by advanced civilizations. As we contemplate these philosophical implications, we must remember that they're not merely abstract speculation. The age of the universe affects how we understand our place in reality, our responsibilities to each other and to future generations, and our fundamental values and goals. Whether we're early or late arrivals in cosmic history influences how we should spend our brief time as conscious beings. If the universe turns out to be older than we think, it would invite us to adopt a more humble and expansive perspective on human existence. We would be participating in a story that began long before we arrived and will continue long after we're gone. Our significance would derive not from being special or central to cosmic purpose, but from being part of an ancient and ongoing process of cosmic awakening and self-understanding. The philosophical implications of cosmic age remind us that science is never purely objective. Every measurement and theory carries with it assumptions about the nature of time, existence, and reality itself. As we continue to refine our understanding of when the universe began, we're simultaneously refining our understanding of what it means to exist within that universe. Perhaps the most important philosophical implication of questioning cosmic age is that it keeps us intellectually humble and open to possibilities that challenge our deepest assumptions. Whether the universe is older than we think, or perhaps timeless in ways we haven't yet imagined, the questions themselves remind us that reality is far stranger and more wonderful than our everyday experience suggests. We began this journey with a simple question: could the universe be older than we think? After exploring the fundamental methods astronomers use to measure cosmic time, examining the puzzling observations that challenge our timeline, and delving into the profound implications of cosmic age for our understanding of reality itself, we arrive at a surprising conclusion. The answer isn't just yes or no. It's far more complex and fascinating than either response would suggest. The universe's age, that seemingly solid foundation of modern cosmology, turns out to be remarkably elastic. Like a rubber band that can stretch and contract depending on how it's pulled, cosmic time bends and flexes under the weight of new observations, theoretical insights, and the fundamental limitations of human knowledge. What appeared to be a precisely determined 13.8 billion years now seems more like a provisional estimate, subject to revision as our understanding of space, time, and cosmic evolution continues to develop. Consider the evidence we've encountered along the way. The James Webb Space Telescope reveals galaxies that appear surprisingly mature for their supposed age, as if they had more time to develop than our standard timeline allows. Ancient stars occasionally seem older than the universe itself, creating paradoxes that force us to question either stellar evolution models or cosmic chronology. The Hubble tension shows us that different methods of measuring cosmic expansion produce conflicting results, with implications that could alter the universe's calculated age by nearly 1 billion years. These aren't merely technical difficulties that better instruments will eventually resolve. They're symptoms of deeper mysteries about the nature of cosmic time itself. Dark energy, that enigmatic force driving cosmic acceleration, might have evolved throughout cosmic history in ways that would dramatically affect age calculations. If dark energy was weaker in the past, the universe would have expanded more slowly, requiring additional time to reach its current state and making the cosmos older than current estimates suggest. The exploration of alternative cosmologies reveals even more radical possibilities. Steady-state models would eliminate cosmic age entirely, proposing an eternally existing universe with no beginning or end. Cyclic cosmologies suggest our Big Bang might be just one event in an infinite sequence of cosmic death and rebirth, with each cycle potentially lasting far longer than our current timeline. These alternatives remind us that the concept of universal age depends critically on our assumptions about how space and time behave on the larger scales. Quantum gravity pushes these possibilities to their logical extreme. If space and time themselves are quantized at the smallest scales, the Big Bang singularity that defines time equals 0 in classical physics might dissolve into quantum foam. The universe could have no true beginning, existing in some form infinitely far into the past. Loop quantum cosmology suggests cosmic bounces that could stretch the universe's history across trillions upon trillions of years, making our 13.8 billion year timeline a tiny fraction of cosmic evolution. The observational limits that constrain our knowledge add another layer of uncertainty to cosmic age. We can only observe a finite portion of what might be an infinite universe, and that portion is filtered through fundamental barriers like the cosmic microwave background. Crucial evidence about the universe's true age and history might lie forever beyond our observational reach, hidden in regions of space and time that will never be directly accessible to human investigation. Yet perhaps the most profound insight from our journey concerns the philosophical nature of time itself. The question of cosmic age isn't merely a technical problem in astronomy. It's a fundamental inquiry into the nature of existence, causation, and temporal reality. Different answers to the age question carry dramatically different implications for human significance, the meaning of consciousness, and our understanding of why anything exists at all. The current scientific consensus holds that the universe is 13.8 billion years old, give or take about 100 million years. This estimate represents an extraordinary achievement in precision measurement, determining the age of everything that exists to within less than 1% uncertainty. The convergence of multiple independent techniques, from cosmic microwave background analysis to stellar evolution studies to supernova observations, provides strong support for this timeline. But science is never static, and our understanding of cosmic age continues to evolve. The Hubble tension suggests that either our measurements contain systematic errors we haven't identified, or our theoretical models are missing crucial physics. The James Webb Space Telescope continues to reveal objects that challenge conventional expectations about cosmic evolution. Future gravitational wave detectors might reveal primordial signals that carry information from epochs earlier than any electromagnetic observations can reach. New physics beyond the standard models of particle physics and cosmology could fundamentally alter age calculations. Modifications to gravity might affect cosmic expansion in unexpected ways. Additional dimensions predicted by string theory could influence how space and time behave on cosmic scales. Quantum effects that we don't yet understand might play crucial roles in cosmic evolution that would change our entire perspective on cosmic time. The possibility that dark energy itself evolves over cosmic time remains one of the most intriguing frontiers in cosmology. If dark energy was different in the past, whether stronger or weaker than today, it could resolve many of the puzzles we've encountered, while simultaneously altering our understanding of cosmic age. Future surveys by space telescopes and ground-based observatories will test these possibilities with unprecedented precision. But even as we push toward ever more accurate measurements and sophisticated theoretical models, we must acknowledge the fundamental limitations that constrain human knowledge of cosmic time. Some barriers may prove absolute. We may never directly observe the universe before the cosmic microwave background epoch. The quantum gravitational regime that governed the earliest moments after the Big Bang may remain forever beyond experimental verification. The portions of the universe beyond our cosmological horizon will never be directly accessible to observation. These limitations don't diminish the scientific enterprise. They enrich it by reminding us that reality is far more complex and mysterious than our current understanding suggests. The elastic nature of cosmic age reflects the dynamic, evolving character of scientific knowledge itself. Each new observation, each theoretical insight, each technological breakthrough has the potential to stretch or compress our understanding of cosmic time. The practical implications of cosmic age uncertainty extend beyond academic cosmology. If the universe is older than we think, it would have had more time for the complex processes that led to stars, planets, and ultimately life itself. The apparent fine-tuning of physical constants that allows complexity to exist might be less miraculous and more natural if there was more time for different configurations to be explored. The rare events that led to our solar system and the evolution of life on Earth might be more common in a universe that had additional billions of years to work with. Conversely, if the universe is younger than current estimates suggest, it would compress the timeline for cosmic evolution and make our existence even more remarkable. The rapid formation of galaxies, the quick production of heavy elements, and the early emergence of potentially habitable planets would all require more efficient processes than current models assume. We would live in a universe that was incredibly dynamic and fast evolving in its youth. The search for extraterrestrial life and intelligence takes on different character depending on cosmic age. An older universe would have provided more opportunities for life to emerge and evolve into complex technological forms. The galaxy might be filled with the remnants of ancient civilizations that rose and fell long before our solar system formed. Our apparent cosmic loneliness might reflect not the rarity of life, but our late arrival in cosmic history. The ultimate fate of the universe also depends critically on its age and the nature of the physical processes that govern cosmic evolution. Current models predict that dark energy will continue to accelerate cosmic expansion, eventually leading to a cold, dark, empty cosmos where stars burn out and black holes evaporate. But if dark energy evolves, or if there are cyclic processes we don't understand, the long-term future could be very different. An older universe operating according to cyclic principles might undergo periodic rejuvenation, with new phases of cosmic evolution replacing the current expanding epoch. Quantum effects might eventually recreate complex structures even in an apparently dead universe, leading to new eras of cosmic awakening and consciousness. The heat death that seems so final in current models might be merely one phase in an endless cycle of cosmic death and rebirth. As we contemplate these possibilities, we must also consider how advancing technology might change our perspective on cosmic age. Artificial intelligence might help us analyze vast data sets and identify subtle patterns that reveal new insights about cosmic evolution. quantum computers might enable simulations of cosmic processes that are impossible with current technology. Future space missions might provide observational capabilities that dwarf even the James Webb Space Telescope. The merger of astronomy with other fields could also transform our understanding of cosmic time. Biology might reveal how life processes constrain the conditions under which complexity can emerge. Computer science might show us how information processing and computation relate to the fundamental structure of space and time. Philosophy might help us understand what questions about cosmic age actually mean, and which aspects of time are real versus constructed. But perhaps the most important lesson from our exploration of cosmic age is the value of intellectual humility. The universe has repeatedly surprised us, revealing phenomena like dark energy and cosmic acceleration that no one predicted. Our current understanding of cosmic time, impressive as it is, almost certainly contains gaps, errors, and misconceptions that future discoveries will reveal. The elastic age of the cosmos reminds us that scientific knowledge is provisional, subject to revision as new evidence emerges and new theoretical frameworks develop. This isn't a weakness of science, but its greatest strength. By remaining open to the possibility that our current models are incomplete or incorrect, we position ourselves to discover truths about reality that are far stranger and more wonderful than anything we currently imagine. The universe may indeed be older than we think, or it might be younger or exist in a fundamentally different temporal framework that makes the question of age meaningless. What matters is not the specific answer, but our continued willingness to ask the question, to challenge our assumptions, and to follow the evidence wherever it leads. In the end, the cosmos keeps time according to rules we're still learning to read. The 13.8 billion year age that anchors modern cosmology may be just our current best guess in an ongoing conversation between human curiosity and cosmic mystery. The universe's true temporal nature, whether older, younger, cyclic, eternal, or something entirely beyond our current conception, awaits discovery by future generations of cosmic explorers. The elastic age of the cosmos stretches across scales of space and time that dwarf human experience, reminding us that we're part of something far grander and more mysterious than we can fully comprehend. Whether the universe is older than we think, or age itself is the wrong question, the cosmos continues to reveal new secrets about the nature of existence, the time, and our place in the grand cosmic story that began, if it began at all, in the unimaginably distant past.